Welcome, everyone. All right, so we're going to be looking at, we're kind of going back, and this is kind of a review section here. And this is just seeing how we can read graphs of derivatives and see what the graphs of f prime and f double prime tell us about the original function f. So this is kind of just putting together a lot of the things we've already talked about. So we're going to see what to do if we're given the graph of f prime. What information can we uncover about the original function f? And we'll see that we'll be able to do intervals of increase-decrease, intervals of concavity, local extrema, and inflection points. And then if we're given the graph of f double prime, well, we'll see how to do the intervals of concavity and the inflection points. So again, a lot of this is review. Actually, most of this is review, but we're just kind of putting together all the pieces here. So let's just review what the first derivative, some of the things we can use the first derivative for. So if we have an interval a to b, or maybe a to infinity, or minus infinity to b, or something like that, and we find that f prime is positive, so if f prime is positive on that interval, well, then we can immediately conclude then that the original function f is increasing on that interval. And when f prime is negative, the original function f is decreasing. So by looking at our first derivative, figuring out where it's positive and negative, we can figure out where the original function is increasing or decreasing. And we have something similar involving our second derivative for the intervals of concavity. So when our second derivative is positive, our function's concave up. And when it's negative, our function is concave down. All right, so let's actually start with the easier case here. Let's start with our second derivative. We're not going to get quite as much from our second derivative. So let's look at example 1. We're given the graph of f double prime. And we want to uncover as much as we can about the original function f. So the graph that we're seeing here, this is not of function f. This is of f double prime. All right, so what are we going to try to do here? Well, we're going to first try to figure out the open intervals where the original function f is concave up and where it's concave down. And then once we have those intervals of concavity, we'll be able to figure out where we had an inflection point. All right, so let's do our sign chart for f double prime. Really, that's what we're trying to do for the intervals of concavity. So let's plot our x-axis. And what are we going to plot on here to begin with? Well, we want to figure out where f double prime is 0 and where f double prime is undefined. And in our case here, this is a nice graph. There's no open dots or anything like that. So the second derivative here is equal to 0 at, well, where? When is our second derivative equal to 0? When it crosses the horizontal axis. So our second derivative is 0 when its graph crosses the x-axis, and it crosses the x-axis at x equals 0 and at x equals 3. And our second derivative is never undefined in this case. So there's no open dots or anything like that. Okay. So there's no open dots or open missing points on this graph. All right, so these x equals 0 and x equals 3, these are the places where we might have an inflection point. So now these are any x value we'd get here, this is what we'd plot on our sign chart. So we're going to plot x equals 0 and x equals 3. And what these do is they split up our x-axis into 3 intervals. And what we want to do is we want to figure out what is f double prime doing on each of those intervals. So let's first look at this interval from minus infinity to 0. So that corresponds to this section of the x-axis. So if we look at this section of our x-axis and look at what the graph is doing, the graph over there is above the x-axis. So that means all the f double prime values are positive. And we can immediately say then that our original function f is concave up on that interval. Now if we go to the next interval, in between 0 and 3, so now this is kind of this section of our x-axis. So we're looking at all the points on our graph in between x equals 0 and x equals 3. Well, we see that we're kind of on this section of our parabola. And so all of the points on this section are below the x-axis, so they're all negative. And when our second derivative is negative, it means concave down. And then finally, for that last interval, going from 3 to infinity, we're over here. And if we look at the kind of the points on our graph, they're all above the x-axis. So they're all positive, which means our function is concave up over there. All right, so we were able, by looking at the graph of f double prime, we were able to figure out where f double prime was above, where it was below, and it was above again. And when it's above the x-axis, when it's positive, that means the original function f is concave up. So notice we're not answering concavity for this graph. This graph is always concave up. What we're doing is we're given the graph of f double prime, and we're kind of recovering what the original function f looked like. So we can state our intervals here for concave up. So f is concave up on the interval from minus infinity to 0 and on that interval from 3 to infinity. And the original function f is concave down on that interval from 0 to 3. Okay. Now for part 2 of this, we want to find the x values where function f has an inflection point. So remember, an inflection point usually happens when the second derivative is 0, and what has to happen is there has to be a change in concavity. So if we look at our sign chart, we go from concave up to concave down right there at x equals 0. So there is a change in concavity. And then there's also a change in concavity at x equals 3. We go from concave down to concave up. So both of these x values that we found, there is a change in concavity at each of those. So x equals 0 and x equals 3. Okay. Well, let's try another one. Let's look at example 2. Now for this one, we're given the graph of the first derivative, f prime, and we're going to want to kind of uncover information as much as we can about the original function f. So again, the picture that we have here, this is not the picture of f, this is the picture of f prime, its derivative. And let's see what we're going to do. We're going to find the open intervals where f is increasing, decreasing. And actually, maybe even before then, we might even get the critical numbers of f. And then we'll also be able to classify those critical numbers as either a local max, local min, or neither. And believe it or not, we're also going to be able to figure out the intervals of concavity by looking at this first derivative and then the inflection points. All right, so let's start with the intervals of increase. So again, when we do the intervals of increase here, we want to do the sign chart for f prime. So let's start by drawing our x-axis. and then we're going to see the sign of f prime and what that tells us about the original function f. Now, what are we going to plot on this sign chart? Well, we want to plot where f prime is 0 and where f prime is undefined. So let's look at our kind of the usual places here. Where is this first derivative 0? Where is it undefined? And again, for when we're looking for f prime equal to 0, and remember, we're looking here at the graph of f prime. So we want to figure out, when does this graph cross the x-axis, or when does it touch the x-axis? And so to figure out where f prime is 0, given the graph of f prime, we're looking for where does it touch the x-axis. And we see 3 places here. So this happens at x equals -3, 0, and 2. And f prime being undefined, that would happen if there was a hole or a missing point on our graph. So something like, maybe like that. We don't see anything like that on this graph, so none. Okay. So -3, 0, and 2, these are the points we're going to plot on our sign chart. And what they do is they split up our x-axis then into 4 intervals. And to get the intervals of increase, decrease, all we're looking is we're trying to figure out where is f prime positive and where it's negative. So if we look at this first interval, -infinity to -3, that gives us this section of our graph. So we're on this section of our x-axis, and if we look there, the graph is above the x-axis. So f prime is positive there. Now if we're looking in between -3 and 0, now that takes us to this section of our f prime graph. And we see that it's below, so negative. And then from 0 to 2, it's above, so positive. And then from 2 to infinity, the graph gets negative and just stays negative. It's below the x-axis. So f prime is negative on that interval. And we have our sign chart now, so we can say what the original function f is doing. So it's increasing on that first interval, decreasing on the second, increasing on the third, and then back to decreasing on that last one. All right. So we can start answering the question. So we want to know, where is the function increasing and where is it decreasing? So let's list our intervals. So f is increasing on the interval from -infinity to -3, and on the interval from 0 to 2. And then it's decreasing on the interval from -3 to 0, and on that interval from 2 to infinity. So we're able to get our intervals of increase, decrease here. Now, what are the critical numbers? Well, the critical numbers for function f are where the first derivative is 0 and the derivative is undefined. So these values that we find here, these are actually the critical numbers. So we actually found 3 of them. So remember, the critical numbers are where the derivative is 0 or undefined. And in this case, all of them worked out there. Okay. Now, what is part 3? We actually want to classify these critical numbers. So remember, critical numbers are where the original function might have a max or a min. These are the only places where it might have a max or a min. And we have 2 tests that we can use to figure out what's going on. Well, we could use the second derivative test, but in this case, we don't have any information about the second derivative. So we have to use the first derivative test. And it turns out we've already done most of the work for the first derivative test. So let's go on up to our sign chart. So for our sign chart, that's really the work that we need for our first derivative test. And then we just have to interpret it. And the way we can kind of quickly interpret it is just get a rough picture of what the original function f looks like. So what we're finding here is that f is increasing, it flattens out, it's decreasing, it flattens out, it's increasing, flattens out, and then it's decreasing again. So roughly this is what function f would look like. And what we see is that at x equals -3, it looks like we have a high point on our graph. So we have a max there. At 0, it looks like we have a low point, so we have a min there. And then at x equals 2, it looks like we have another high point. So we can classify these. X equals 3. We have a local max at x equals -3. We have a local min at x equals 0. And then we have a local max, again, at x equals 2. Now, we don't have enough information here to find the y-coordinate for what these maxes and mins are. So all we can do is just locate them. Where do they actually happen? And just tell what's going on. So we don't actually have enough information to find the y-coordinates for these. All right, so part 4, this might be a little new. We want to find the open intervals where f is concave up, concave down. How can we do this? Well, let's just go back. Maybe something we haven't done yet. So let's think about what it means to be concave up and concave down. So we know that's related to our second derivative. So where our second derivative is positive and where it's negative. And if we go up to our first derivative, we know that for our first derivative, if we know where the first derivative is positive, that tells us where the original function f is increasing, and when it's negative, it tells us where we're decreasing. So there's another relationship here, kind of relating our first derivative and our second derivative, putting it all together. And that is, if we have the first derivative positive, what this tells us is that the original function f is increasing. And when our first derivative is negative, that tells us that the original function f is decreasing. So that's what this says. Just kind of simplifying it. Now, what happens if we apply the derivative to these statements, essentially? So there's an equivalent that says if f double prime is positive, then that means f prime is increasing. So we can look at where f prime is increasing. So if f double prime is positive, that means f prime is increasing. And if f double prime is negative, that means f prime is decreasing. So to figure out the intervals of concavity, we really need to know where is f double prime positive and where it's negative, but we can also look at where is f prime increasing and where is f prime decreasing. So it's going to be enough if we look at f prime, the graph of f prime, we can just figure out where f prime is increasing and where it's decreasing. So let's try this out. So we have this graph. And let's see if we can do our sign chart for f double prime. All right, so we want to figure out where f double prime, where f prime is increasing and where it's decreasing here. and that'll tell us about f. Well, actually, that'll tell us about f double prime, and then that'll tell us about f. All right, so we want to figure out for f prime, looking at this graph, ultimately we want to figure out where f double prime is positive and negative. And that matches up perfectly with the intervals where f prime is increasing and decreasing. So let's look for the intervals of increase-decrease for this graph. And we notice them. It's decreasing, and we're going to be estimating here, so things aren't perfect. But it looks like we hit maybe like 1.7 is where we hit this low point. And then same, it looks like we hit a high point right around there. So it looks like if we're interpreting the graph here, remember now we're trying to figure out where f prime is increasing, decreasing. Before, when we did this original one, we were trying to figure out where f, the original function, was increasing, decreasing. So now we're trying to find where f prime is increasing. And so this we could just look at the graph. So we see that it's decreasing here. So it looks like up to about negative, we'll say negative 1.7. And it looks like f prime is decreasing on that interval. And then on the next section, it's increasing, it's moving up. And it looks like the high point happens around maybe like 1.2. So we'll say 1.2 here. So it's increasing on that next interval. And let me get out of the way here. And then finally, once we get past that high point on this graph, function f prime starts to decrease again. So it's decreasing. And so when f prime is decreasing, that means f double prime is negative. And when f prime is increasing, that means f double prime is positive. So we're just kind of going in reverse. Normally we say when something is negative, then that implies decreasing, and when it's positive, that implies increasing. We're kind of going in reverse and saying that when it's increasing, that implies positive. And then same thing for decreasing over here. That means f double prime is negative. But now since we know where f double prime is positive and negative, we can say what's going on with our function f. So we're concave down, then concave up, then concave down. So we're able to answer the question then. Our intervals of concave down, well, we have this interval minus infinity to negative 1.7, and then 1.2 to infinity. And then concave up is right there in the middle, negative 1.7 to 1.2. So we're concave up on that interval negative 1.7 to 1.2, and concave down. And we're talking about the original function f here. And we're concave down on minus infinity to negative 1.7 and on 1.2 to infinity. And at this point, we have enough information to figure out where the x values, where the original function f has an inflection point. So again, we're looking for where do we change concavity. And if we go up to our sign chart for f double prime, we see that we actually change concavity twice. We go from concave down to concave up, and that happens at, about negative 1.7. And then we also go from concave up to concave down, and that happens at 1.2. So that's where we have two inflection points, negative 1.7 and x equals 1.2. All right, so let's try one more of these. So let's look at example 3. And for example 3, we're given the graph of f prime here. and we want to recover as much as we can about what the original function f is doing. All right, and for that, we're going to do the intervals of increase, decrease. We're going to find and classify the critical numbers, and then we'll also be able to get our intervals for concavity, so concave up, concave down, and any inflection points. So let's start with our sign chart for f prime. All right, so that's what we want to start with. We want the intervals of increase, decrease. So that means we're going to do a sign chart for f prime. And well, we draw our x-axis. There it is. And we just want to find all the places where f prime is 0 and where f prime is undefined. All right, so f prime being undefined, that would happen if there's like a hole or a missing point on our graph, and we don't see anything like that here. So there's none of that. Now, when we want to look for where f prime is 0, again, this is the graph of f prime. So we just want to see where does it cross the x-axis. And if we're looking, we see, well, there's a point there, point there, point there, and we touch the x-axis there, so that's going to count. So it looks like we got 4 spots. We got x equal to -4, x equal to -1, 2, and then 5. All right, so we got 4 places where our graph of f prime touches the x-axis. So those are going to be the 4 spots that we plot on our sign chart here. Okay. So then we want to figure out what f prime is doing on each of those intervals. So we have the interval from -infinity to -4, -4, -4 to -1, -1 to 2, and then from 2 to 5, and from 5 on to infinity. All right, so we got all of that, all those intervals to check here. And so let's start with the very first one, -infinity to -4. So if we look, here's our intersection point at -4, and if we kind of look to the left, our graph of f prime is below the x-axis, so that means it's negative. And then from -4 to -1, that means we're looking on this section, and we see that our graph is above, so that means f prime is positive there. Then we go to below, so negative on the next interval. Then we're back above, so positive. And then at x equals 5, we just touched the x-axis, so f prime is 0 there. But then if we go to the right side of it, we're still positive. So positive over here. So what that means is f goes decreasing, increasing, decreasing, and then increasing and increasing. All right, so we have enough information now to kind of answer the first part. We have our intervals of increase, decrease. So the original function f is increasing on the interval from -4 to -1, the interval from 2 to 5, and then the interval from 5 to infinity. And then f was decreasing, if we go back to our sign chart, f was decreasing on the other intervals, -infinity to -4, -1 to 2, and that's it. So there were 2 intervals of decrease here. All right, and kind of along the way, we actually found the critical points, the critical numbers here. So we found 4 critical numbers. So x equals -4, -1, 2, and 5. So we actually got 4 critical numbers here. So now we can classify these using our, again, we have to kind of use the first derivative test here to classify these critical numbers as either local max or local min. And that's because we've already done most of the work for this. So we're going to use our first derivative test. All right, so let's kind of draw, or let's look at our sign chart. So a way to, again, kind of remember what the first derivative test says is you can just draw a rough picture of what your function, what the original function f would look like. So in our case, it's going to be decreasing, and then it flattens out, and then it becomes increasing. Then it flattens out, becomes decreasing. Then it flattens out, and it's increasing, and then it flattens out, and it keeps on increasing. So it looks something like this. And so what we see is just by getting a rough picture of what the original function f would look like, we have a min at -4, then we have a max at -1, then a min at 2, and then we have neither at x equals 5, because at x equals 5 the graph does flatten out, but it's uphill in one direction and downhill in the other direction. So x equals 5 would be neither here. Another way to kind of think of this is if we want to go back to what the first derivative test actually says for local extrema, we're just looking at f prime. So if f prime changes from positive to negative, we have a max. And if f prime changes from negative to positive, we have a min. Again, I think it's easier to just kind of remember to draw the picture. And if f prime does not change signs, well, then it's neither. It's neither a max nor a min. So if there's not a sign change going on at a critical number, it's neither max or min. And what we end up with is kind of like this plateau, like we're seeing here. So we plateau at x equals 5. All right, so let's write that out. So at x equals -4, is a min, x equals -1 is a max, x equals 2 is a min, and x equals 5 is neither. And again, we can just interpret that from our first derivative, our sign chart of our first derivative, by just drawing in decreasing, flattens, increases, flattens, decreases, increases, and then keeps on increasing. So we go from a min to a max to a min to neither. Okay, so for the last part of this, almost there, we just want to get our intervals of concave up, concave down. So this is where we want the sign chart for f double prime ultimately. And for our sign chart for f double prime, we want to look at where f prime is increasing and where it's decreasing. So when we do this, we're going to figure out where f prime switches from increasing to decreasing or vice versa. So if we look, for the very first section here, f prime starts off increasing, and then it looks like it stops right at x equals -3. So -3 is going to be the first kind of x value that we plot here. And f prime is increasing on that first interval. Then it switches to decreasing, and it looks like maybe around like negative or x equals 0.3 or something like that. So 0.3 will be the next number that we plot on our sign chart. And on there, f prime, the graph of f prime is decreasing. Then from there to about 3.2, the graph is increasing again. And then from 3.2 to 5, it's decreasing. And then from 5 onward, it's increasing. All right, so we have our sign chart or we have what f prime is doing. Now we want to relate this to what the sign of f double prime is. And when f prime is increasing, that means its derivative must be positive. And when it's decreasing, it must mean its derivative has negative sign. And now we know what f double prime is doing. We have the sign chart for f double prime, so now we can say what f is doing. So the original function f is concave up on that first interval, concave down on the second, concave up, concave down, concave up. And so let's write out the intervals for concavity here. So concave up, is those 3 intervals, and concave down are those 2 intervals. So the original function f is concave up on the interval from minus infinity to -3. So that was the very first one. And then from 0.3 to 3.2, and then from 5 onward. And then it was concave down on everything else. So the interval from -3 to 0.3, and the interval from 3.2 to 5. All right, so for the last part, we just want to know where are the inflection points. And the inflection points happen when we change concavity. So where do we actually change concavity here? Well, we change at each of these. So we go from concave up to concave down at -3. We go from concave down to concave up at 0.3. And then same thing, we change at 3.2. And then we also change concavity at 5. So all of those kind of places where we sliced up our sign chart here, those are all going to be inflection points. All right. So just kind of a nice review, looking at graphs of f prime and f double prime and seeing what information we can recover about the original function f. So all the information, we were able to find out all this information about f using just its graph f prime. So we get a pretty good idea of what that original function is doing. All right, so that's gonna do it. So enjoy the rest of your day, and we'll see you on Wednesday. Bye-bye.